Thank you. Hello, so everyone, and good afternoon. Well, I am from Turkey and Ege University. Today, I would like to talk about the forensic investigation of question documents by X-ray photoelectron spectroscopy via chemical imaging. This is a very new and recent technique. That's why I would like to just share our experiences with you. First of all, let me just remind you what a question document is. It can be any document written by a source or authenticity which is doubtful, and forensic examiners handle different kinds of question documents like letters, checks, contracts, insurance claims, suicide notes, lottery tickets, etc. These can be listed more, and which can be found in a variety of criminal investigations. Here are some of the tools used by forensic document examiners. I'm sure most of you know these kind of techniques or tools. For example, a digital microscope or an optical microscope with infrared or UV waving scopes, and some other basic tools. Actually, in literature, you may encounter some novel techniques for question document examinations. For example, the methods in forgery and alteration in the documents are becoming more increasingly and more sophisticated. And forensic examinations of these question documents routinely involve physical and chemical analysis of those inks. And X-ray photoelectron spectroscopy is also a very attractive and novel technique for ink analysis, since it can discriminate the chemical differences easily and rapidly. And one of the advantage of this technique is being it's non-destructive to the evidence, and it does not require any sample preparation. Before going through our results, I would like to just briefly mention about the principles of X-ray photoelectron spectroscopy. By photoelectron spectroscopy, which is XPS, you can investigate the surface chemistry of any materials. It gives quantitative information, and it extracts information about 1 to 10 nanometer of the material. It uses ultra-high vacuum, and you can detect every element greater than lithium. So, what information can you obtain from XPS is that the identification of elements near the surface, local chemical environments, oxidation states of transition metals, valence band structure, and morphology of thin films. And by using just point XPS, you can understand the surface chemistry. And by imaging XPS, that I'm going to go ahead with that, you can locate it on the surface. And by depth profiling, you can understand the variation from the surface to the bulk. Well, in such an XPS spectrum, you see some very sharp peaks. So how do we obtain those sharp peaks? You just send X-rays, and the inner electrons, photoelectrons, are ejected, and these photoelectrons create some sharp peaks like this. These are the photoelectron peaks of any elements. The chemical shift in X-ray photoelectron spectroscopy gives us a very important information about the chemistry of the materials. The chemical shift is the change in binding energy of a core electron of an element due to change in the chemical bonding of that element. Effects that cause this chemical shift in XPS spectra is the oxidation state, covalent structure, neighboring electron withdrawing groups, and anything that can affect ionization or orbital energies. Well, what about the surface chemometrics? It deals with the spectra produced with the XPS. You can just make identification and classification by surface chemometrics. For example, what chemicals are present on the surface can be determined, and where they are located. Apart from this, which group does it belong to, and what are the differences between the groups? So, Chemometrics also deals with principal component analysis, which is the analysis of variability in a particular set of data. For example, in order to measure a sample, you need set of variables that describe them. So, principal component analysis is a very powerful tool for analyzing the data. It reduces the data to lower dimensions with minimal loss of information. The relationship between the samples and variables are discriminated, and the first few principal components explain maximum variance. Now comes the next important question: what does best express the data mean? Well, you see the variances and ignore the components of less significance. For this reason, in the first, for example, in the first principal components, you get all the required information. For example, take a look at this woman's picture. This is an original grayscale image, okay? And when someone asks you, how can you just tell about this lady? For example, what do you see dominantly in this picture? Here you can see that there are almost 30 principal components that describes this lady's picture. But when you look at the first 5 principal components, you can see that the ratio is very high. So, and take a look at this in this side. First principal component, you do not see anything, it's blurry. And 5 principal components, you see more or less there is somebody in the picture with a head and hair. And as the number of principal components increases, the picture is seen much better and you see what is there in the picture or image. So how about the typical application of surface chemometrics? Surface chemometrics says that this is this in the located picture. So what does it say? Principal component, mostly chemometric technique. It's a pattern recognition technique. In PCA, images are produced with an entire spectrum for each pixel. For example, just take a look at this picture. Each color is represented by any spectrum. This can be XPS, Raman, FTIR, or any other spectroscopic techniques that gives you a distinct signal. So by these signals, you collect lots of spectra, and by using chemometrics, you just pick up the data required from this picture. So how about the chemical imaging using principal component analysis? You can assess the compositional inhomogeneities in a sample materials, or estimate and assess the trial sample composition, and consider the possibility of multiple compounds in sample. This is a typical XPS instrument, and this is a typical survey spectra obtained from an XPS. And here below you see an alpha image. For example, we have put an alpha with a pen on the aluminum foil, and we have just applied principal component. First principal component says that the red one is aluminum foil, and the green part is the ink on the aluminum foil. Basically, principal component analysis application by using XPS says in the image. In the present study, this is a very preliminary and pilot study, and this demonstrates the great potential of XPS by providing an overview of its application to forensic examinations of ink evidence from needle pens. And in addition, it presents the chemistry of problematic intersecting lines with different pens. In this study, we have analyzed 3 different trademark blue needle pens by XPS. And of course, we have used an A4 copier paper routinely that we use in our daily lives for printers or for writing. Well, we have just analyzed the paper, regular paper, and we have seen that it is It contains carbon, nitrogen, oxygen, sulfur, and calcium along with sodium in its structure. And take a look at this. This is the carbon partial spectra of the just regular paper. That we have done this in order to eliminate the background signals. And then we have analyzed blue needle pens by XPS. So here you see 3 different blue needle pens were analyzed by XPS, and then chemical imaging was done by intersecting lines using XPS on the changed area. We have used Uniball, Pilot, and Xray blue pens in this study. And here you see we have made point analysis from each of them, and we get a survey spectrum, which means that what elements are present in this point sample area. More or less based on the background signals and the signals that come from the ink, says that we have carbon and nitrogen, sulfur, calcium, and sodium in our samples. Please pay attention to the carbon spectra here on the right side of each ink pen, blue needle pen. You see there's a spectra and there's a different pattern in the carbon spectra of each of them. So this means that XPS can discriminate the differences between these blue pens because their chemistry differ from each other, since the inks used in each pen will be different from each other due to the trademark. By imaging and using principal component analysis, we have just made a 3 at first, and then just made and turn it into 8. That is the document forgery mostly encountered. Well, here you see that when it is chemically imaged by XPS, one can easily understand that different types of pens are used. Here we see 3 principal components. Red one is the A4 paper, and this greenish one is the pen used with Xray's trademark. And then someone has just changed this into 8 with another blue pen, which is a Pilot. And here are different principal components. And when you overlay all of these images, you get such a spectra. And this is not an just something that you do with your eye, as in the case of microscopic techniques. This is a chemical image. That's why it's really important. Another example is that maybe you cannot discriminate the colors, because when the chemistry of the materials look like each other, the colors may be very close to each other. And again, this is just a line like 1, and then it has been turned into 7. And in this one, we have used Uniball to turn it into 7. So here are the principal components, and this is the overlaid images. Consequently, we can say that developing more informative and effective tools for question document examinations become more necessary. And since XPS can differentiate the chemistry and quantity of materials based on their bonding, many types of question documents could be rapidly examined by XPS. Here we have proven that with our preliminary results, XPS was a very novel technique, and there will be great demand on this research area in future. Its major advantage is its being non-destructive to the sample, and it's a very rapid technique that you can get information very easily in a very short time. And greetings from Turkey and Izmir. Thank you for your attention and listening.